Okay, in the previous video, I told you that I would like to improve the numerical efficiency of my implementation, and the key was just to changing uh, optimization level of my compiler. So I didn't use any of optimization option. But when I switched to the uh, -O2 option, so it drastically improved the numerical efficiency. So of course I made another change in my code, but the most important one was just changing compilation option. So now I think that it is much faster. So why don't you just start this example so it doesn't take long, so just during it is learning, so let me just explain what happens in it. So now that was fin. Yes, we make the fin. After that we fill STI. So all over our entire simulation domain. After that we do fin cut. This fin cut is performed to have the isolation between the Nmos region and Pmos region and other logic gates. So here we introduced two different separated regions. So one is a lower one and one is a upper one. So they are corresponding to three fins, and there is also three fins. So except for this region, so everything is just etched away. In this model specification, actually I etched away only fin material and STI material. Therefore, the substrate material is not etched away. But in reality, uh, even this substrate is significantly etched, but please understand this is in this emulation it is just left to improve the numerical efficiency because you know the thickness of our substrate is not that thick, so I don't want to make any kind of problem with this one. So now fin cut is performed. So after that, we have two islands of silicon, and they are separated by this fin cutted layer. And after that, we do also once again fill this erased part with STI once again. So the level of STI is just matched to the STI for fins. So initially we had fins and STI, and this newly fabricated STI is just grown up to this part. So now we deposit the dummy uh, dielectric material. So that is the end of a fin cut of stat CG and S. After that, we do once again dummy gate patterning. So here we have a dummy gate pattern. In reality, once we make a deposition and do patterning, but we just unify into just to here what it did is exactly same. Uh, we deposit first dummy gate isotropically. After that, we etch following this pattern. These patterns are corresponding to each vertical line for dummy gate. Yes, and that is saved as dummy.cgns. After that, we perform this spacer formation. So locate material. is deposited and etched. In this etching, we do it anisotropically. So now we have side wall spacers, and that is saved as spacer dot cgns. With the help of improved numerical efficiency or faster the code, I was able to perform this 10-pin system without much problem. So let me just show you the result of this one. Yes, first go to this STI formation result. So we expected 10 pins, and 10 pins are separated by STI. Okay. Okay. So as expected, now we have 10 pins, and there are STI layers, and yes, in this case there is no pin cut is performed. Thing. Uh, but now we do this pin cut. Now let's do it. Go this one. Now we have pin cut result. Um, so here you can see that this purple one is corresponding to the dummy gate. So before this one, so now we have a cutted pin, and once after pin is cutted, there is nothing like this. These parts are gone. However, we do again the STI growth, so that's the reason why we have finally having this quite flat planarized STI layer. Please note that here actually we can see substrate region, but as I told you before, when we perform the fin cut, actually this substrate is also etched away, but that is just limited here for simplicity. So please regard this part and this part as just STI once again. After that, the mitigate is the sorry dummy dielectric material is uh, deposited. Now we have these two islands of fins. After that, we will draw this vertical, the, this we will draw this vertical gate lines. So let's do it. When we do it, so I said that is a save that is dummy.cgns. When we have a look at that one, okay, now you can see that here we have so three dummy gauge. Now it is quite tall actually. So it is tall, and in reality this is poly, and here even we have a hard mask material. However, that is not considered here. So anyway, this one is should be regarded as masked, and yes, that is the case. And maybe you can see that although this one is quite flat, now here we have some certain difference in its height. So however, it is quite reasonable because so when we just delete this dummy gate, actually here we draw also dummy gate. So since the starting point of our uh, layer is different, one is with the pin, with the pins, and one is without any pin. So that's the reason why we have now different height. Anyway, now we have a different height, and typically this length scale in this case is 20, 20, 20, and between these 20 wide dummy gate, we have approximately 27 uh, and 20, sorry, not 27, 34, I guess. Yes, so because CPP is set as 54, so now we have just half of it. Now we have dummy gate, and we will perform this spacer deposition. So also let's have a look at the result of this spacer formation. So first it is isotropically deposited, after that etched away. So now you can see that this is the result of spacer formation. So this thickness is corresponding to the initial thickness of our deposition, and I guess that maybe it was 9. So now we have 9, 9 and 34. So now we have a relatively short distance, like 16, and in this case 8. And anyway, this is the case for our FinFET or fabrication procedure. So this part will be used to later source and drain reason, and we will continue this kind of job with okay. So anyway, now it's time to come back home. Okay, so good night, and I will come back to you with more results. I'm quite happy with this improved speed of my code. Now I hope that my students can enjoy with this code quite a lot. Thank you and bye.